Hello again, it's Jason from STEM Online, where we help uh, students with online math and physics courses, uh, specifically for high school and university. Okay, so today we're going to discuss some more physics concepts instead of math. So we're going to do another physics lesson today, and it's going to be on elastic collisions in 2 dimensions, okay? So the question we want to ask ourselves is, how does this work? Like, how do you determine final velocities in a 2-dimensional elastic collision between two masses, 2-point masses? Okay. So we have mass M1 and M2, let's say, okay? This would be a car collision scenario. Okay, so let's say I have mass M1 on the left-hand side here, okay? And it's making a detour at an angle phi here, okay, with an initial velocity v1, okay, that I've defined here. Okay, so that's the initial velocity of the first car is v1, okay, and it's coming at a diagonal, okay. And then there's going to be mass m2, which is coming from the very bottom, okay, so from the very bottom here all the way at the bottom and coming directly upwards. It's going vertically. Okay, so mass m2 has a velocity v2 and it's going vertically upwards. Okay, so how do we get started here? Well, the way to determine the final velocities in a 2-dimensional elastic collision is using conservation of momentum. Okay, so we're going to use conservation of momentum, which states that the momentum before the collision, before the two objects collide, is equivalent to the momentum after. Okay, so we have to state that P initial is equal to P final. Okay, so P initial equals P final. Right? Then on the left-hand side, this is the sum of all the momentas on the left-hand side, because it's this is in reality saying P initial total, same as P final total. That might be better notation. So P initial total is going to be equivalent to mass m1, right, times v1, okay, v1, right, plus mass m2, okay, mass m2, v2. So this is the sum of the momentas before the two cars collide, okay, and this is equivalent to mass m1 v1 prime, where prime will denote after, right? So after the collision, what happens to object's one's velocity, okay? Plus mass m2 v2 prime. Okay, that's normally what we need to do here. Okay. However, though, since it's in a 2-dimensional scenario for this elastic collision, we need to decompose it into xy coordinates. Okay. So we're going to take this equation here and put it in x coordinates first, okay? So I should be saying, let's do the x components first. Let's say x components will be this one. Components, I will highlight this. It's x components. So just to be organized, it's good to have label the x components here, okay? So the x components, okay, for your conservation of momentum equation. And you should also put subscripts of x's everywhere. Okay, so that way you're not getting confused. Okay, I'm putting x's everywhere. So x component. Okay, so what do we do next? We need to draw what is happening here. Since mass m1 is moving with velocity v1 at a diagonal to an angle phi here, an angle phi, I'll draw a diagram on the right hand side here to zoom in. Okay, so let's say you have, so here is v1, yeah, v1 would be like this. Okay, so v1 mass m1. Okay, so this is vector v1, and we all know that vectors contain components, xy components. So I have a y component and an x component. Okay, so my y component would be like this. This would be labeled v1y, and my x component would be v1x. Okay, and then I also have to draw my inclination angle. I will call this angle the angle, the initial angle that is coming in, that the car is coming in with before the collision. I'll call it angle phi. Okay, so this is little phi here. Okay. Okay, so you can see here, based off what's going on in the collision, that there's trigonometry involved here based off the vector diagram. Okay, so we need to replace the v1x and the v2x's with some expression here. Okay, so v1x, what is that going to be? Well, if you look at the diagram, v1x is the adjacent component to the angle. Okay, so v1x is equal to v1 cosine phi, right? Because cosine is defined as the adjacent side or the adjacent component, the velocity component, with the hypotenuse here, right, of v1. Okay, now that I have this, I will substitute it in, right? I'm going to substitute into my momentum equation here, right, for v1x. Do the same thing for v2x, okay? Now, be careful. You need to organize your diagrams. What I mean by that is, obviously, it's very important for all physics problems to start off with a geometric diagram so you can translate the diagram into quantities and variables and then hopefully into equations. Okay? But you have to have the right diagrams and the right thing that's going on. Otherwise, it's not going to make sense. The equations won't make sense if you don't have everything in order. So we have diagram 1 here, okay, for V1. Now we need a diagram for V2, okay? Let me just label this diagram 1. Diagram 1 here, okay? Then we have diagram 2. Diagram number 2. Diagram number 2 is for car number 2 that is moving with an upward vertical velocity, right? V2, okay? So I'll just draw this. So this is my V2, okay? What you'll notice here is, since the car is moving just in one direction, it only has a y component. There is no lateral motion whatsoever, so there's no horizontal component to the velocity. It's 0, okay? Alright, so we can say on the left-hand side of the momentum equation for x component, m1 v, this is going to be, by the way, this will be negative because this is a negative x-axis over here, okay? So this is going to be negative m1 v1 cosine phi. Be careful with the directions, right? Since we're on an xy Cartesian plane, the left-hand side should be negative, the right-hand side is positive. Up is positive, down is negative. Okay. Alright, what do we substitute for v2x? v2x is 0. So this is now plus m2 times 0. Okay. Right, so that's what we have for our x component equation so far for the conservation of momentum. Now if you look at the right-hand side, the v1x prime, well, we need to figure out what that expression is, and we need to make a correct diagram, okay? All right, so diagram 1 that we did was for before, right? This is before, corresponding to mass m1. Diagram 2 corresponding to mass m2. That was before. Okay. Now for diagram, I'll call the next one diagram 1 after. What I mean is after the two cars have collided. Okay. So diagram 1 after. Okay. Diagram 1 after looks like this. Okay. So if you look at the xy plane here, we're going to have our magnitude vector here, v1 prime. This is the velocity after the two cars have collided, v1 prime. And I'll call the angle after theta. Okay, so theta will be over here. And me see, v1, yeah, theta would be over here. And this is the x component. We have to know what our x component is. So v1 prime x is located over here. Okay. v1 y prime is over here. v1 y prime. Okay. Let me just make some room here. This is angle theta over here. Yep. Okay, so now we have the diagram 1 after. Okay. And we're going to have to make a diagram 2 after as well, right? So diagram 2 corresponds corresponds to the mass m2 after it is collided with mass m1. What happens to its velocity components? Okay. Alright, so let's look at this now. This is going to be, well, as you can see here, mass m2 now, once it collides with mass m1, right, what's going to happen is that it's just going directly, it doesn't completely eject, it goes vertically upwards. So this one over here, diagram 2 now, right? Okay, so diagram 2 will look like this. Okay, so we have diagram 2 like that. Yeah, and it will be moved like this. So v2 prime is like this. Okay, I'll call v2 prime with a vector. Okay, so we have diagram 1, diagram 2, diagram 1 after, diagram 2 after. So we can, based off the drawings, we can substitute the correct corresponding component equations into our conservation of momentum equation for the x components, which we're doing, and then we'll do the y after. So we've already substituted v1x, v2x, let's do v1 prime x. That's v1 cosine phi. So m1, let me see here. Oh, sorry, not that one. Look at diagram 1 after. So v1x prime here, right, is going to be the adjacent over the hypotenuse. So it'll be v1 prime, right? v1 prime is equal to v1 prime x cosine theta. Okay, so we're going to substitute this into v1 prime x. Okay, and since the component is going to the right here, the x component, it has to, in order to have a vector v1 prime going upwards, the v1 x prime has to go to the right for the vector diagram. Okay, so m1 v1 prime x cos theta plus m2 v2 prime x. Now looking at v2 prime x, let's be careful with this. v2 prime x would be over here. Yeah, it's going vertically upwards still, so there's still no component for v2 prime. Okay, so v2 prime x is 0 because there's only a y component afterwards. Okay, multiplied by 0. Okay, this simplifies our equation because there's zeros here. 2 minus m1 v1 cosine phi equals m1 v1 prime x cosine theta. Okay, now you'll notice that the m1s will cancel. Okay, there is no m1 here because they're divided on both sides. This is now minus v1 cosine phi is equal to v. Yes, it's going to be, let me see here. That's a v1 prime. v1 prime is equal to v1 prime cosine theta. Okay. It's very important when you do these problems is to take your time and keep track of all the drawings. Otherwise, it's very easy to make a mistake. Okay, because you won't have if you don't have the correct corresponding drawing for the correct corresponding equation, the whole thing will be messed up. Okay, so we simplify down to this now. Okay, so this is a v1 prime. Okay, alright, so we have this. Alright, so we want to solve for v1 prime here. Okay, so what I need to do is I need to divide both sides by the cosine theta. Okay, so this should be minus v1 cosine phi. Okay, cosine phi divided by cosine theta. Okay, cosine theta. Do it on both sides of the equation. Okay. And what you're left with is that v1 prime is equivalent to minus v1. Minus v1 cosine phi over cosine theta. Okay. I will highlight this because we just solved half the problem. We figured out the final velocity after for car 1. Okay, that's the expression. Now we need to do it for car 2. Okay, so car 2 will more likely, we have to, since we have two vehicles here, we're going to have an x component to the equation. We'll also have a y component. Okay, so let's do the y component. So y component of the conservation of momentum. Okay, so this would be PIFY equals PIY, sorry, momentum before, right? So initial momentum before in the y direction. Okay, so momentum before in the y direction is equal to the momentum after in the y direction. They have to be equal because this is the conservation of momentum. Momentum is never lost. Okay, going back to the diagram, right, and writing out our equation, this would be m1v1y plus m2v2y equals m1v1y prime. This is the velocity after in the y direction for car 1 plus m2 v2 prime, velocity after in the y direction for car 2. Okay, now replace what v1y is. Okay, well, v1y will correspond to diagram 1, right? If you've been paying attention, you're looking at this diagram, right? We drew it earlier. This corresponds for the y component as well, right? For the vector v1 as the object is about to make impact, before impact. So v1y here, the equation would be simple, right? It would be v1y is equal to v1 sine phi. And the reason for that is because it's the opposite over the hypotenuse, okay? So now that we have that, it's going to be m1 times. Now here's the thing you need to be careful with your signs. Always keep track. This would be a negative v1 sine phi because the y component of the velocity is going downwards. It needs to correspond to the xy diagram. So this is minus v1 sine phi. Okay, m1 minus v1 sine phi. Next part here is the v2y. Okay. Well, v2y, let's look here. Yeah, v2y. So there is a y component here, okay, for v2, but that's corresponding to mass 2. Okay, so v2 is corresponding for the velocity of mass 2, and since mass 2 is moving vertically upwards, there's only a y component, so we substitute that with the v2. Okay, so plus m2 v2. Okay, and then on the right hand side, the velocities after the collision for mass 1 and mass 2 in the y direction. So this would be m1 v1y prime. Okay, let's look at v1y prime. That's corresponding to mass 1 after the collision between the two vehicles. v1y prime, okay, let's just be x here, just 1 second. X prime, v1 prime. So the v1y prime in this diagram here, right, if you look at it, is going to be equivalent to positive, right? So positive v1 prime sine theta. And the reason for that, why it's positive, is the fact that this velocity after is going upwards after the collision. So v1y prime is positive. Substitute that into the momentum, conservation of momentum equation for the y direction. So that would be, let me see here, v1 prime sine theta, v1 prime sine theta plus m2 v2y prime. Now the v2y prime, let's see here, is also, that corresponds to diagram 2, that is the mass 2 after the head-on collision between the other vehicle. Afterwards, what's happening to its velocity for mass 2? It also is going vertically upwards, so we replace with v2. Okay, to v2. Alright, so now we just need to algebraically simplify the equation. Now it's very straightforward. So minus v1 sine phi plus m2 v2 is equal to m1 v1 prime sine theta plus m2 v2. Okay, so remember what we're looking to solve for here, right? Looking to solve for the v2 prime. Okay, we already found v1 prime, but we need to find an expression for v2 prime, because that's what the question was asking for. So to do that is, looking at the y component of the collision equation, rearrange everything. So move this over here, subtract both sides by m1 v1 prime sine theta. So then I'm left with m2 v2. m2 v2 is equal to, m2 v2 is equal to m2 v2 prime, sorry, m2 v2 prime. M2 v2 prime is equal to m2 v2 minus m1 v1 sine theta. M1 v1 sine theta. Was that theta? Yeah, minus m1 v1 prime sine theta. Careful, sine theta minus m1 v1 sine theta minus m1 v1 sine phi. Okay. Now we're going to solve for v2 prime. Okay. So to do that, divide everything by m2. Okay. So to v2 prime to m2 v2 minus m1 v1 prime sine theta minus m1 v1 sine phi. Divide by m2 here. Obviously, if you split this up, v2 prime equal to v2 minus m1 over m2 v1 prime sine theta minus m1 over m2 v1 sine phi. Okay. So we figured out the equations for v1 prime and v2 prime. Okay. And that is how you solve a elastic collision problem to determine the final velocities of the collision. I hope you enjoyed this video. There'll be plenty more of math and physics videos. So like and subscribe, and see you next time.